Okay, so we are very happy today to have Professor Noah Snyder from Indiana University, Bloomington. He earned his PhD from US Berkeley in 2009 under the supervision of Nicolas Richetier. As an NSF postdoctoral fellow at Columbia University, he was mentored by Yang-Baxter. Since joining Indiana University in January 2013, he advanced to associate professor in 2017 and now professor. His research focuses on example-driven questions in quantum algebra and quantum topology, with a particular interest in the classification, topology, and arithmetic of fusion category and subfactor. Today, we talk about interpolating conformal embedding. Noah, please.
Thanks so much for the very nice introduction. Thanks for the invitation to speak. So I'm going to tell you about interpolating conformal embeddings. This is a preprint that we have up on the archive that's joint with Kane, Edie Michel. And so if I'm going to tell you about interpolating, I fixed the title, but I didn't fix this slide. So I'm going to tell you about interpolating between conformal embeddings are a special kind of quantum subgroups. So I'll tell you a little bit about that as we get there. But I'm going to have to tell you about interpolation. I'm going to have to tell you about quantum subgroups and conformal embeddings. And then I'm going to combine all of these and tell you about a new category that interpolates between certain quantum subgroups or conformal embeddings. So let me start out with some background about this general idea of a Deligne interpolation. So the idea here is that you start with some discrete family of tensor categories that depends on some parameter n. So the kind of example you should have in mind here is the category of representations of GLN. There's one of those for every n. But the idea is if you have a family that depends on this parameter n, and the Hom spaces between tensor powers of some favorite object stabilizes as n goes to infinity, then you can try to build a continuous family that depends on this parameter t that could be any complex number instead of just a natural number. Okay, so for example, for GLN, the stabilization phenomenon is Scherr-Weil duality that tells you that these Hom spaces are described by some group algebras of the symmetric group, okay? So this is something that's been done a lot, and I will walk you through what happens for GLT, but the main examples to have in mind are GLT, the general linear group, OT, ST, the symmetric group, and the quantum versions of GLT and OT. So I'm going to start out by just motivating where this GLT comes from when t is not necessarily an integer. And to do that, I want to start with a description of what GLN is. GLN is the universal group with a representation of dimension n. That is to say, a representation of a group of dimension n is the same thing as a map to GLN. Okay? So that's what GLN is. If I want to try to generalize that, I can't easily generalize this to make n something that's not an integer because a representation has to have dimension that's a positive integer, okay? But the idea is, what if you replace groups with symmetric monoidal categories, okay? So symmetric monoidal categories still have a notion of dimension, but that dimension doesn't have to be an integer, and they generalize the category of representations of a group, okay? So instead of looking at the universal group with a representation of dimension n, I'm going to look at the universal symmetric tensor category with an object of dimension t. Okay, and that's what I'm going to call GLT diagram. I'll explain on the next slide why I put this little diagram here, but this is the version of GLT that we care about for this talk. Okay, so GLT diagram is supposed to be the universal symmetric tensor category with an object of dimension t. Well, the amazing thing is that actually is relatively easy to describe because there's a diagram calculus for maps in a symmetric tensor category. So if I have a symmetric tensor category with an object I can write that object by a strand oriented upwards here. Its dual is the strand oriented downwards. And because it has a dual, this is some co-evaluation morphism. This is this is the symmetric structure. And this whole thing is just some composition of evaluations, co-evaluations, and symmetric structures. So if I have any symmetric tensor category, I can make sense of a picture like this as being a map from X, tensor X dual, to X dual, tensor X, tensor X, tensor X. So any of these make sense. Linear combinations of them would also make sense if I was in a tensor category. And the dimension being t says anytime you see a circle, you can remove it for a cost of t. Okay. Now, the important thing to know about this is that this tensor category is not too giant. The endomorphisms of the unit object are spanned by closed diagrams of this form. And it's not hard to convince yourself that if you have a closed diagram like this, using that it's symmetric and using that you know the value of the circle, you can always reduce it to just a scalar. Okay, so that's what GLT is. It's just the category where the objects are strings of up and down arrows, and the morphisms are linear combinations of pictures like this, modulo this relation, where composition is vertical stacking and tensor product is putting things next to each other. Okay, so that's all GLT is. Any questions so far?
Yeah, I have a question. In fact, when you consider GLN, in fact, you are in the world of fusion category, but with GLT, you have infinitely many simple objects. You are,
Yeah.
so it's
Yeah, that's right. GLN, you would already have infinitely many simple objects, but for GLT, you have somehow even more. They grow really fast, so they're not even what's called uh, moderate growth. Yeah, so the size of the Hom spaces grows faster than factorially. Yeah, so they're much bigger categories. When T is generic, if T is not a positive integer, then this category will be semi-simple, but it will have infinitely many simple objects. Other questions?
it's okay.
Yeah. Okay, so let me give you some warnings. If I take GLN diagram as defined on the previous page, that has a map to rep GLN because this is the universal symmetric tensor category with an object of dimension n, and this is a tensor category with an object of dimension n. So there is a map like this, but this map is not an equivalence. And the reason is that in rep GLN, the n plus first wedge power is 0. And in this diagram category, we didn't put in anything saying the n plus first wedge power is trivial. Okay. Now you shouldn't be too surprised that this is different from that because I can tell you some other tensor categories, symmetric tensor categories with an object of dimension n, namely the category of representations of the supergroup GLN plus k slash k. The defining object of that has dimension n plus k minus k. The k's cancel, and that has dimension n. Okay, so when n is an integer, this category is a little bit different than rep GLN. And furthermore, if n is an integer, there's a harder thing to build called GLN abelian, which is an abelian tensor category. And I'm not going to need them at all in this talk. I just want to warn you that if you go to other talks on Deligne categories, often the hard part is building this abelian category out of the diagram category. And I'm just not going to bother with that in this talk. But for the case of GLN, you can see what's going on. This GLN abelian is an inverse limit of all of these GLN plus k slash k's. That parenthesis is at the wrong spot. GLN plus k slash k reps of that. Okay, and this paper, there's a paper by these three authors that constructs GLN abelian in this way. There are other constructions of an abelian category that, and they're all equivalent to each other, but yeah, I'm not going to get into the abelian case. I only care about the easier diagram version. Okay, but one thing I will care about is the quantum version of GLN. So you may recall that rep GLN has a Q deformation, which I'm going to call GLNQ. This is some category of representations of the corresponding quantum group. And I would like to know, is there something like GLTQ, some deformation of the category of the category GLT? And here there's a very good candidate, which is instead of looking at symmetric tangles mod this circle, I look at braided tangles mod the Homfly relations given here. And this is like a quantum Schur-Weil duality. And this lets you describe a category GLTQ that depends on two parameters, T and Q, that's a quantum version of GLT. And we will need this later in the talk. Okay, so that's the background on Deligne interpolation. Before I leave the topic of Deligne interpolation, I want to tell you a few key ideas that will be important later on. Okay, so the one that we've already seen is that the key thing in building an interpolation category is to give a uniform skein theoretic description, to give some skein theoretic description that doesn't change as you vary n. Okay. It can change in a boring way, right? Like we had this value of the circle was t, that t changes, but the form of the relations doesn't change as you vary the parameter. So the second thing is, if you look at these descriptions that I've given, say this one, look at tangles mod the Homfly relations. This is describing something by generators and relations. And whenever you describe something by generators and relations, it's often very hard to know that it's non-trivial. If you write down a group by generators and relations, usually you'll write down the trivial group, and there's no good way to know whether your group is trivial or not. And the same thing happens for tensor category. If you write down a kind of random skein theory, you'll just get the zero category and nothing interesting, okay? And in general, it's very hard, given some skein theoretic description, to figure out whether it gives you a non-zero category or not. In general, this is quite difficult. There are a few cases where it's been done, and Zhengwei has one of them, but there aren't so many of them. So showing that a skein theory is consistent, that is to say that it's non-zero, in Deligne interpolation settings, you can often do this for free by showing that it has infinitely many consistent quotients. So what you say is that when n is one of these special values, this quotient's on to rep GLN. And I know the category rep GLN is non-zero. And then you can make a little algebraic geometry argument that says if a polynomial identity holds infinitely often, then it holds always. If two polynomials or even two rational functions are equal to each other infinitely often, they're automatically just identical to each other. And so what you can do is you could show that this skein theory gives you consistent evaluations by saying it gives you consistent answer for infinitely many values and hence has to agree always. Okay. And finally, you have to be careful to avoid determinants. So there's a thing that's GLT, but there's nothing that looks like SLT. And the reason is that SLN has a determinant map, a map from the nth tensor power to 1, satisfying certain properties. And that n has to be an integer because it's a power of an object. You can't take the 5.5 power of an object in a tensor category. So there's no good way to build an SLT interpolating between the different SLNs because the determinants look different as t varies. But GLT does make sense, so that will also be important for us later. Okay, that's all I had to say about delete interpolation. We're about to go to the next section, so maybe I'll pause again and see if there are any questions or comments.
Yeah, in fact, maybe a nice question, but is there a relation between delete interpolation and some what's called a free quantum group like Banica and Wang you start from?
Yeah, that's a good question. I think I think what is true is that some of the free quantum group constructions, like the free symmetric group, in turn have their own interpolation category. That is to say, you can define like the free symmetric group, just like you can define the ordinary symmetric group. And just like there's a Deline's ST interpolating between all of them, there is a free ST interpolating between those ones. But I don't think, yeah, so in that sense, Deline interpolation comes up in that theory, but I don't think there's no relationship between like the Deline category GLT and any free version of GL. Other questions?
No.
Okay, so next I'm going to tell you about quantum subgroups or maybe conformal embeddings. Okay. So I'm going to first tell you about quantum subgroups. I only care about, there's some more general things called type 2 quantum subgroups. I'm only going to tell you about type 1 quantum subgroups. And I learned a bunch of this stuff from old work of Agnianu from the 80s and 90s. And here's the setup. Suppose that A is a braided tensor category. Okay. Now, here's two ways you can think about braided tensor categories. You can think that they're E2 algebras in categories. That is to say, they're a category together with a rule for tensoring where you can tensor objects that are put on the plane. This 2 is because it's on a plane. Okay. And the reason that they're braided is that you're allowed to move these around and still get another tensor product. So you can get an iso between x tensor y and y tensor x, but it will depend on whether you braid it over or under. Okay. Or equivalently, you could think of braided tensor categories as being things where the string diagrams take place in 3 dimensions. These are 3-dimensional and this is 2-dimensional because categories themselves have a composition direction. Okay, so you can think of braided tensor categories either as E2 algebras or as things where you can make sense of these string diagrams. And there's a notion of an E1 module over a braided tensor category, which is either in the blue picture here, pictures that you can draw like this. So you can put objects of C in here, and you can put objects in A in here. So C itself should be a tensor category, no longer braided because you can't move them past each other. And it should be acted on by braided tensor categories. So for example, I should be able to take something in C and something in A and multiply them. But then, for example, if I take something in C and something in A, I could multiply it this way, that way, that way, and they should all give you the same notion. Okay? You can also get an equivalent version of this definition skein theoretically by looking at what are the skein pictures that you can draw on a cube like this, where in the red part you use stuff in A, and along the boundary you use stuff in C. Okay? Either of these notions has a purely algebraic description, which is this is the same thing as giving a map from A to the center of C. Because I'm supposed to be able to tensor something in A with something in C, but then I should be able to braid it past by instead tensoring it over there. Okay. So this is the same thing as a what's called sometimes a central functor, a map from A to the center of C. And if you want to see why this notion is related to this notion, you can read a paper of mine with Adrian Brochet and David Jordan. I don't think it's, probably appears other places as well, but that's one place you can read about it. Okay. So this is what a quantum subgroup is. It's a tensor category, no longer braided, that is acted on by the braided tensor category. There is another way you can say this. So Ostrich has this theorem that says a module category is always a category of modules. And this is a special case of a much more general theorem in category theory called the Beck tripleability theorem or the Bar-Beck theorem. And there, what happens is, remember I had this map from A to the center of C. This map has an adjoint, a right adjoint. And if you see where one goes under this right adjoint, it will give you an algebra object in A. And you'll be able to recover C as modules for that algebra. Okay? C will be modules for that algebra. And the kind of algebra that A will be is what's called an étale algebra. It's a commutative semi-simple algebra. Okay. So instead, you could think of type 1 quantum subgroups as just being étale algebra objects in braided tensor categories. Okay. But if I have an étale algebra object in a braided tensor category, I get a new category C that's no longer braided, which is the category of A modules with tensor product over A. Okay, so this is probably the most down-to-earth way to think about quantum subgroups, is they're just commutative algebra objects. Let me give you some examples. If A is quantum SU2 at a root of unity, then the quantum subgroups are classified by the Dinkin diagrams of the form AN, D even, E6, or E8 that have the right Coxeter number. Okay, so SU2 at a root of unity has a fusion graph that's like a type A fusion graph. It looks like, this. And you want to look at the Dinkin diagrams that have the same dual Coxeter number as this graph. Okay, I'll give some examples on the next page. So this whole theory was worked out by Jones, Agniano, and others, and is closely related to subfactors. The language of étale algebras in this setting, this result was also proved in a tensor category setup by Kirillov and Ostrich, but it's heavily inspired by this subfactor results that were earlier. So let me give you an example. So if quantum 5 is 0, that is to say Q is a 10th root of unity, then the quantum group that I have in mind will have this fusion rules. So it has the trivial object, the defining object, and then that one, when you tensor squared, it breaks up as the trivial plus something new. That's quantum 3-dimensional. You do it again, you get something quantum 4-dimensional. If you did it again, you should get something quantum 5-dimensional. But because quantum 5 is 0, following Reshetik and Turaev, you can quotient out by it, and you can get this little category here that is sometimes called the A4 tensor category. And for this example, the only quantum subgroup you can get is the trivial one, A4. That is to say, it acts on itself. This corresponds to the trivial algebra object. But if I did one further, if I did, this one is at a 12th root of unity, so quantum 6 is 0, then you can put an algebra object that looks here and here. You could have done that up here. You could look at an algebra that's here and here, but it won't be commutative. And in this one, it is commutative. And if I look at the category of A modules for it, it does what's called orbifolding. It folds this in half so that the whole algebra becomes trivial. So this guy and this guy make one object. This one and this one make one object. And then this one is fixed, and so it splits in two. And you get what's called the D4 quantum subgroup. So this one has two different quantum subgroups, the trivial A5 one and the interesting D4 one. And if you looked at a 24th root of unity, that would be A11, you would get E6. Okay, so that's what I mean by these quantum subgroups are classified by these Dinkin diagrams. Okay, now that was all for SU2. If you tried to do this for other quantum groups, you start with quantum UQG for some G at some root of unity, semi-simplified. you could ask the same question that we just asked for SU2. So if you fix your Lie algebra G and let Q vary over all different roots of unity, the result is that all the finitely many quantum subgroups are orbifolds. They all look like that folding construction, except for finitely many exceptions that are, E6 and E8 are exceptions. So this was originally announced by Acmianu. There was a nice result of Chopre that got things going again. And Gannon has given an effective version of this that improves on Acmianu's non-effective version. And this is effective enough that it's now been classified in rank up to 6. So if you start with a Lie algebra rank up to 6, we can tell you what all the quantum subgroups, or Terry can tell you what all the quantum subgroups are. Okay, there's one more important thing that I'm going to need before I get to the kind of quantum subgroups that we care about in this talk. And this is this notion of an invertible defect or a Witt equivalence. So recall that if A were just an algebra and M were a module over that algebra, you can as long as that module is nice, if it's finitely generated projective, you can always upgrade it into a Morito equivalence where you put the commutant on the other side. So anytime you have a nice module, there's always a unique thing that you can put on the other side that will upgrade it into some kind of Morito equivalence. And the same thing is true of quantum subgroups. If I start with a braided tensor category here, and I take a module tensor category over it that sits here, there's a unique commutant-like thing that I can put on the other side that will make this invertible. That is to say, we'll make it into a Witt equivalence. And the thing that you put on the other side is the Muger centralizer of A in the center of C. So remember, A mapped to the center of C. It has a Muger centralizer. That's some other subcategory of the center. And that's the braided category that you should put on the other side. In the Barbeck version, the thing that you put on the other side, so here you had your category A with some algebra little a inside, as Roman A inside of it. This is the category of A modules. This thing that you put over on the other side is what's called the category of local A modules. I'm not going to get into what that is, but if you've heard of that before, that's what goes on this other side. Okay, and this is going to be the key technique in proving our main result, is that there's always a thing that you can put on the other side of this boundary. Okay, now the main source of exceptional quantum subgroups, so the quantum subgroups that don't come from orbifolds, well, even the ones that do come from orbifolds, I think basically all of the ones that we know come from a construction coming from equivalently either conformal field theory, vertex operator algebras, or loop groups. And here the idea is you can, if you start with a Lie algebra and a level, there's some vertex operator algebra that you can build called VGK, and its category of modules gives me some category CGK. And then by results of Finkelberg and Kazhdan-Lustig, this category that comes from loop groups actually agrees with the category of representations of the quantum group at an appropriate root of unity. Okay? You have to be a little bit careful about which root of unity. There's a weird change of variables where you have to shift by the dual Coxeter number. But at any rate, the category of modules for vertex algebra is one realization of these quantum group categories. And a conformal inclusion is one VOA sitting inside another VOA in a good way. That is to say, they have the same conformal vector. Okay. Anytime you have this setup where you've got your little VOA and your big VOA will be an algebra in the category of modules for the little VOA. So W will always give you one of these Étale algebras in Rep V. Moreover, any Étale algebra in Rep V can be upgraded into a VOA. Okay? Now, this is actually kind of familiar if you're used to subvectors. So A factor is an extremely complicated analytic object. Similarly, a VOA is an extremely complicated gadget. But once you start with a factor, as soon as you have a finite index algebra object in the category of bimodules for that factor, you automatically get an overfactor. That is to say, the extra information that you need to give is purely algebraic once you've built this big complicated gadget. So the little VOA is a complicated thing, but to describe the bigger one, W, all you need to do is give an algebra object in rep V. Okay. Moreover, rep W is the category of local modules for that algebra A. So whenever you have one of these conformal inclusions, you know what rep V is. That's your original category A. You know what rep W is. That's your category of local modules. That's the thing that appears on the right-hand side of this picture. So you know A and you know the category of local modules. There is some category C sitting in between the category of A modules, but its structure is somewhat mysterious and hard to read off from just knowing about the VOA. Okay, so there are going to be lots of these conformal inclusions, and we're going to know that they give you quantum subgroups of rep V, but we're not going to know much about the structure of those quantum subgroups. Okay, example, the E6 quantum subgroup of SL2 comes from a conformal inclusion SL2 level 10 into SP4 level 1. All right. Now, for this talk, you don't need to know much about VOAs, and I know that because I know basically nothing about VOAs. One thing you do need to know is that there's a list of all the conformal inclusions. So I always look this up in this Davidov, Muger, Nikšić, Ostrich, Wick group paper that has a table at the end of all of these inclusions, but they are pulling from some earlier work in the physics literature that gives complete lists of these. Okay, so you can just look up what the lists are. So now we get to our problem, and this is a problem that I learned about from Zhengwei. Look at these lists and see if there are families. So excluding the orbifold families, there's basically 4 interesting families of these up to level rank duality. So there's this thing called level rank duality that means each of these come up twice. I don't really want to get into that. But yeah, so there's SLN at level n plus 2 sitting inside this guy. Then there's SLN at level n sitting inside SO n squared minus 1. And I want to point out this n squared minus 1 is just the dimension of SLN. Okay? So the next 2 look like that as well. Instead of SLN, you have SO or SP, and on the right-hand side, you take SO of the Lie algebra. That is, you say, take SOD, where D is whatever the formula is for this dimension. I just didn't want to write it down because it's kind of a mysterious formula, but it's literally just the dimension of that Lie algebra. And here's our question. Is there a Deligne interpolation for the determinant-free version of, so remember, these all have SLs in them, or SOs, and we already knew you can never Deligne interpolate when determinants are involved. So you should replace this with some version where you looked at GLN and O. So is there a Deligne interpolation for the determinant-free version of these discrete families? And so for the first answer, the first one, the answer is yes. And this is a result of Zhengwei Liu in his paper, Yang-Baxter relation planar algebras. For the second family, that's what I'm going to talk about in this talk. And we think we should be able to do the third and fourth in a similar approach to what's in this talk, but Kane has a student working on this. So you should not work on it, but we're getting near that. Okay, so that's the end of section 2. I'm now going to tell you about the new interpolation category, but maybe I'll pause for a moment and see if there are questions.
In fact, I have a very nice question. Can you
Yeah.
briefly recall the definition of a quantum subgroup at the level of a general tensor category? I guess you say something.
Yeah. So it's, I mean, the algebraic definition is the simplest one. A quantum subgroup is just a tensor category C
Yeah.
and a map from A to the center of C. That's the simplest definition.
So what is
I think of it as using these kinds of pictures, that it's the kind of thing that you can put on the wall of a braided tensor category.
so here A embed into the center of C?
Yeah, then we would say C is a quantum subgroup of A.
Okay. And
What you're supposed to do is think of this map as being like restrict and tensor. If I had a group and a subgroup, I can restrict and tensor, and that gives me some kind of action of the big group on the little group, and that's analogous to this one. For actual groups, everything involved is a symmetric tensor category instead of braided, so it's a little easier. You would just get a restriction map it would just be a symmetric tensor functor. But here it's a little bit more complicated. You need the central structure.
okay, thank you.
Yeah. Other questions?
No, not.
Great. Okay, so right. So now we want to build our new interpolation category. So the idea is we're going to analyze, remember what's going on here is that we have our category A and then we have a wall that's our category C, and then we can put on the other side this wit equivalent category, this commuton, okay? So in our case, the category that it's a subgroup of, the one that goes in this black part here, is supposed to be, where was this? This was quantum SLN at level n. So it should be some Homfly category, but at a very particular value of Q. Okay. And one way you can, well, a very particular value. Remember, Homfly has two parameters. Because I want it to be SLN level n, I should get down to just one parameter. And one way you can do that is just saying this twist is supposed to be I. Okay, so you can write down just the Hecke, this is the usual Hecke algebra relation. The twist should be I, and then this one follows from the rest of them. Okay, so that's the thing we're taking a quantum subgroup of. And then the thing that should go on the other side is, remember this SON squared minus 1 thing. If n is odd, this is like a Z mod 2 cross Z mod 2 pointed category. And if n is even, it's the Ising category. Either way, there's a Z mod 2 subcategory. And Z mod 2 means the Z mod 2 category is a red strand. Because it's invertible, it satisfies this skein relation. And this one just says the circle is equal to 1. It's 1 times the empty diagram. That is just the circle is the empty diagram. These are the skeins that Z mod 2 satisfies. Okay? So what you should have is that the blue category should consist of pictures that are a mix of black and red, where the black comes in the front, the red comes in the back, but they might be allowed to interact in some way along the blue sheet. And that's the hard thing, is you don't know how they interact with each other along the blue sheet. Okay? But the lucky thing is we're going to find one way that they can interact along the blue sheet, and that's going to be the only way that they can interact. So proposition, this object G appears inside X tensor X dual, where X is the defining representation of SL. So this tells us that one way that things can interact is you can have an X tensor X dual on the front hitting the wall in the middle and then having a red strand come out the back. That's what it means that X tensor X dual contains a copy of this object G. This is not hard to prove. It takes a little bit of combinatorics of Frobenius reciprocity. The reason it's relatively easy is that this 1 plus G is related to the free fermion vertex operator algebra. I don't want to get into exactly where this comes from, but this is one of the only spots where you really need to know a little bit about your vertex operator algebras, but the amount you end up needing to know is extremely small. We just need to know this kind of an interaction. As an aside, if you're doing Zhengwei's family instead of ours, there's a similar thing, but the orientation is a bit different. G sits inside X tensor X now, and that means it no longer needs to be self-dual. This guy is automatically self-dual because it's sitting inside this X tensor X dual, which is itself self-dual. But here it's X tensor X, which won't be self-dual. So you have a red strand for G and a red strand for G inverse. And again, they can only interact at a trivalent vertex, but the orientations look different at that trivalent vertex. Okay, so it is possible to describe Zhengwei's family using pictures very similar to the pictures that I'm going to do in our example, but the arrows will go slightly different directions. Okay, so here's our definition. Let EQ be the tensor category spanned by diagrams that look like this. So they can have red strands and black strands, and those can interact in this way where you can have a red strand hitting two black strands like this, modulo some relations. So we have a bygone relation. The normalization of that is pretty easy to work out because you just take the trace of both sides and then use that oh, if the black strands don't have arrows on them, that just means the relation holds for any version of the arrows that works. So here there's a version where it goes up like this. So let's see, that would be up, 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 and then this one would need to be, up as well. And then there's a version where they all go down. Okay. Rademacher 1 through 3, the Homfly relations, we already talked about that. This red strand is symmetrically self-dual. And here's the interesting and important one. You have a braid relation that lets you move black strands over red strands and over trivalent vertices, but you can't do it the other way. You can't move black strands under red strands. Red has to be under black, not over black. And the reason is just that that's the structure of these pictures, right? The black stuff is on the front, the red is in the back. They freely braid that way. This is just always how quantum subgroups work, is that the stuff in A can braid over the stuff going on in C. And similarly, the red stuff only braids under things. Okay, so that's the confusing point, but this is how all quantum subgroups work. Quantum subgroups always have this thing where there's a braiding that goes over, but not under. Some easy ones. So the fact that G is non-trivial tells you that this part of the picture here, where you have a red going to nothing, since G has no maps to 1, that has to be 0. And since G was invertible, you get a relation like this. So none of these relations are hard. They're all essentially automatic. And that's the miraculous thing. All these relations basically had to hold, and we just write down diagrams of this form on these relations. And at first glance, you might not think that these are enough relations, but they actually are. Okay. So that's the definition of our category. So any questions? This is the new category. Okay. Here's our first theorem. If Q is e to the 2 pi I over 4n, then if you take the Karoubi completion and the additive completion and semi-simplify and do a de-equivariantization. So de-equivariantization goes between GLN and SLN. Then this category that you get So SEN is the category that you get by specializing your continuous parameter to be the right root of unity and then completing semi-simplifying and de-equivariantizing. Then this agrees with the quantum subgroup category. Okay. And then our second result is that the dimensions of the Hom spaces are always 2 to the n minus 1 times n factorial, which is not 0. And in particular, this is not the 0 category. Okay, so we really do get a new category that really does interpolate between all these quantum subgroup categories. The proof of one, so it's easy to get a functor from SEN to CN. This is essentially what I just said was that like, you know, all those relations are satisfied, right? Like it's easy to get that all of these relations hold in CN. To show that it's full, you need a classification of subalgebras of A. So that's where we actually use some VOA stuff. But the idea is that if this functor weren't full, it would give you a different quantum subgroup. And we know all the quantum subgroups. So you just check that it can't be as like a Galois theory argument. Like whatever the image of this functor is has to come from some quantum subgroup, and then you just look at all of them and see that it can't come from anything else. Faithfulness uses that you're semi-simplifying and that Cn is unitary. So this is sort of automatic from the fact that Cn is unitary, that it's faithful. So that's how you prove one. And the way that you prove two is you show that it spans by a certain evaluation algorithm. This evaluation algorithm is basically a fancy version of the Homfly evaluation algorithm. And you show that that set of diagrams, so you write down in a specific collection of 2 to the n minus 1 times n factorial diagrams. You show that they span by using an explicit evaluation algorithm, and you show that they're independent by looking at quotients. That is to say, you show that they're linearly independent at infinitely many specializations. And if there were, and that means that they have to actually be linearly independent. If they were dependent, you would be able to see that in the quotients. So these are our two main theorems. There's actually a third theorem, which I'll mention briefly. Endomorphisms of x to the n is actually a well-known algebra called the Hecke-Clifford algebra. Okay, so this is a little calculation. It's kind of interesting. The way that it works is like you look at pictures of this form essentially. You look at ladders of this form, and then you figure out what relations they satisfy, and they satisfy, you have this generator and you have the crossing, and you try to figure out what relations those two things satisfy, and they satisfy something called the Hecke-Clifford algebra that has been studied for a long time because it comes up in something called Sergeyev duality in studying quantum supergroups of type Q. So the fact that these endomorphism algebras are the Hecke-Clifford algebra, we prove in our paper, but we don't do anything with it. But Kane, together with Hans Wenzel, has used this to actually prove lots of results about, and this is also up on the archive now. They prove lots of results about these categories, what all the simples are, the dimensions of all the simples, and the basic fusion rules. That is the fusion rules for tensoring with X and tensoring with X dual. They're able to completely answer all of this using essentially the fact that these Clifford algebras were somewhat well understood before. You have to add a bunch more because the Clifford algebras weren't really studied at roots of unity, and you have to study a new trace on them. So there's a lot of interesting stuff going on, but it's this connection with the Hecke-Clifford algebra that makes what they do work. And I should point out that these results are interesting even for the non-interpolated categories. That is to say, if you wanted to understand the combinatorics of the quantum subgroups at the actual special values, the actual normal quantum subgroups, this is the best way to do it. prior to this, I don't think it was known like what the simples will look like, what the fusion rules look like, what the dimensions were. This approach is new, both for the interpolation category and for the special values. It's sort of interesting. The last thing I'm going to say is that there's this type Q, also called isomeric or queer Lie super algebras. They have a quantum version, and Alistair Savage worked out what their diagrammatics looked like. You can do a slightly different version of the diagrammatics. He describes a super category. I'm going to describe an ordinary category. You have the standard representation, and then you have the odd line. The odd line is an invertible red object that's self-dual, but now anti-symmetrically self-dual. And if you just look at his relations and compare them to ours, they look the same, except our twist had an I, and his twist doesn't have an I, it has a 1. And otherwise, the relations are basically the same, except this twist relation now forces the circle to be 0. And there's a pretty unimportant thing that this rotation becomes -1. Okay, but this being 0 changes everything because it means the category is not semi-simple. But what I want to get at is that the type Q skein theory, which is where the Hecker-Clifford algebras looked like, if it came from, looks a lot like our skein theory, but not exactly the same. And the categories are very different. Our category is semi-simple. The objects have non-zero dimension. The type Q categories are non-semi-simple. Lots of things have dimension 0. It's only the endomorphism algebras where all the arrows go up that look the same. As soon as you start having arrows that go down, they start looking very different from each other. This is a bit of a mystery. I don't understand why these things are related, but maybe I'll end by commenting. It seems like maybe Zhengwei's family has a similar analogy to the type P paraplectic skein theory. And again, I have no idea why. Okay. I think that's all I had to say. So thanks again. Yeah, I'll stop here.
Thank you. Thank you very much. So, question.
Yeah.
Let me start just. So the family of you mentioned is it what you said? It's a determinant-free version of this conformal embedding, and you said it's relevant to make interpolation, but you did not. Did you mention the interpolation version of your family, or you just mentioned the family and then you said you can interpolate?
Oh, this is the family. So this has a continuous parameter Q. So it is a continuous family. And then this theorem is the theorem that says it interpolates. So if you set Q to be one of the special values, and then you de-equivariantize, de-equivariantizing is exactly this killing the determinant, then it will agree with the quantum subgroup category. So that's the sense in which it interpolates between the existing ones. But yeah, this is an interpolation category. I mean, it's just a one parameter, continuous parameter family of categories. So it's just a family of categories. The sense in which it's an interpolation category is exactly this theorem one.
And therefore, so the category in theorem one is it finite in the sense of category?
Yeah, that's right. These quantum group categories, these quantum subgroup categories are fusion categories.
Okay.
Yeah. This category is not a fusion category. If Q is generic, it's semi-simple, but it would have infinitely many simple objects. But these special ones, when you take specialize to an nth root of unity and semi-simplify, these ones are fusion categories.
And they are not symmetric, of course.
but they're not new. Well, okay. I mean, people knew that these ones were quantum subgroup categories. Some of the combinatorial results about them from Kane and Hans's paper, that is new, but the existence of those categories was not new. But this interpolation category, that is new.
Yeah. I mean, the family SEN it's a braided fusion category.
It's not braided. It has again this over braiding. You can draw crossings, but the rule is you're only allowed to move them over things and not under things. So it's not a braided category. Quantum subgroup categories are almost never, they're basically never braided. They always have this subcategory where you can move the pictures over, but the same thing happens like for the right like uh you know uh the AN tensor category is braided. The quantum subgroups, the D evens and E6 and E8, these are not braided. And it's entirely parallel to that situation. The quantum subgroups are never braided. They always have a over braiding. Like you can describe these, like you can describe E6, as like temporally Lie plus a 3 box, where the 3 box or a 6 box, yeah, anyway, depending upon how you count, where the braiding only works for pulling over and not for pulling under. For example, there's an old paper of Bigelow 80E that will explain what kind of pictures you're allowed to do and why they're not braided.
So I have a question about the red strand, this G.
Yeah.
Which category is it in?
Yeah, so the G, this is kind of interesting. I mean, G does give you an object, and so anytime I have an object here, I can build an object in the quantum subgroup by just looking at the free A module.
Sure.
Similarly, I can do the same thing if I start with any object in the back, I can bring it into the middle, okay, by either taking free module. And what's going on here is that I take an easy object in this dual category, and then I move it into here. So it's
not trivial invertible object. You take the free module and the view is from the complete category.
yeah, another way of saying it is it's a local module for A. So if you look at the local modules for A, we started with this algebra in SLN. We looked at the local modules for it, and there was an easy to describe local module. And in particular, a local module is a module. So it gives me an object in the category of A modules.
I see.
Yeah. I think this is somehow the key idea that gets the whole thing rolling is that there's this other nice object. That's the first thing, is that there's this other nice object coming from the commuton. But then the real miracle is that all the ways that the front and back can interact are built out of this one very simple interaction.
And how much relay did you need? From your explanation of the proof, it seems that you need some results about this quantum subgroup or conformal embedding.
Yeah, that's right. We need to know a little bit. We need to know this essentially, that G sits inside X tensor X dual. That's the main thing that we need.
So you still need relay to do this. Okay.
And this is a little calculation. It's not a hard one, but it's not, it does require knowing a little bit about the VOA.
I see.
The other thing we end up needing to know about quantum subgroups is that is this step here where it's full by the classification of subalgebras of A.
Right.
Though I should say, suppose this failed, suppose the functor wasn't full, you would have still built an interpolation category between some quantum subgroups. It would just have been some other quantum subgroups than the ones you thought you were doing. So that would be fine. It also can't happen because you know all of the lists of examples, right? It's like,
yeah, but for other things that we don't know, maybe this method give you new quantum subgroups, right? You try to do some interpolation, then you can find some new things.
Yeah. I mean, somehow it's like maybe to get this subgroup, I needed to allow this interaction and some more complicated interaction. That's possible, but it turned out just allowing this one was enough.
That's it. Thank you.
Yeah, and for this step, we use some old papers on VOAs. We just like use some paper that describes them. The reason it works out so nicely is because of this connection to the free fermion VOA.
I have a very nice question. Can you explain the motivation for interpolated category in the sense of in what it is interesting, in what it can like?
That's a fair question. I mean, honestly, I don't know that there's been like really big applications of them. They're sort of nice in that they tell you that, they tell you things like the dimensions of simple representations of GLN are always rational functions in N, which is kind of interesting. I mean, they give you examples of tensor categories with properties that you might not have known would happen. So for example, the sizes of the Hom spaces grow faster than the Hom spaces for rep G do for any G. So they kind of tell you that the world of tensor category, but possible tensor categories is bigger than you might have realized. But yeah, I don't know, like, why someone who's not a tensor category person would care about delete interpolation. It's kind of nice, but it's, yeah, I don't think it has like a slam dunk practical application.
Well, I have a quick comment about this. There's one advantage for the interpolation. Computing the fusion rule at the roots of unity is very challenging. But computing the fusion rule for the interpolated family is actually much easier. And there are systematic methods using the symmetric polynomials as characters and computing somehow generating functions for those kind of characters, and that can be used to produce the fusion rule. And this method just won't work well if we just look at roots of unity, but works pretty well for generic parameters. And then we can look at the reduction to reduce the fusion rule by looking at the characters on certain spectrum. So I think that's one kind of advantage to look at the interpolated family. And this really go back to like the Schur duality. Like if we want to just compute the fusion rule for SUN or for symmetric group, it's actually not easy for their representations. But if you look at the Schur duality for the generic case, the fusion rule are much easier, like characterized by Schur polynomial. And then we look at the quotient. I think in that sense, it's just it's an advantage of computing such interpolated family. And another thing is for the computation of the quantum dimension, it's also very difficult for just any particular example at a certain root of unity. But once you know the characters, symmetric polynomials, then the quantum dimension is just taking the symmetric polynomial at such a like very special position. and then you get the value. So that gives you the formula for quantum dimension. Those are, and also computing those characters just in general, it's much easier for the interpolated one, but not easy at root of unity. Just it's kind of general phenomenon.
Hmm.
I have another question, which I'm actually quite curious about this connection between. Well, here is a connection between quantum subgroups and the conformal embeddings. And in early days, Feng-Xu used that to construct E6 and E8 from conformal inclusions using the alpha induction methods of commutative Frobenius algebra. But there's another connection that's the one-to-one correspondence between symmetric spaces of Lie groups and conformal embeddings. And for symmetric space, that's a purely classical geometric subject. And it's another like mysterious that we have the right level for the conformal embedding if and only if this embedding comes from symmetric space. And this is, I think, it's the early work of maybe it's mentioned in the paper of Katz. I'm not sure whether it's proved by him. Just did you get any chance to see the connection between those very nice subgroups and the categorical data with those geometric objects in symmetric space?
Yeah, nothing that I know of, but I haven't really thought about it. That's an interesting question.
Yeah. I have a question regarding another kind of interpolation. I don't know if you have heard about my paper with Zhengwei and Liu, where we interpolate PSL2Q. We have the final group PSL2Q, with Q is a prime power, and we, at the level of fusion ring, at the level of character ring, we can interpolate that to the family where Q is not prime power. Did you see this paper?
I haven't read it carefully, no, but yeah.
I just wanted to know if
I'll give it a look and if you could send me an email with the link, I'll give it a look and get back to you. Yeah, but somehow this one, I mean, the whole trick here is this idea is really special to these quantum subgroup categories, because the whole trick here is this idea that like you already have an interpolation category here, and then you just add one more object and one interaction. And so I don't know that this really had like it's very much I feel like it's kind of special to this setup of quantum subgroups. I don't know whether I expect a similar thing to, yeah.
Well, let me make a comment on the non-Sebastian's question. So there we look at the PSL2 sigma P. We have this group, and then we can look at its representations. And then somehow we have an interpolation of the fusion ring for P like equal to 6. This certainly is not a group. But what's the interesting part is if we take such groups and then we look at the representation category and then look at its gene field center. And then for the Frobenius algebra, the canonical one in the gene field center, that algebra, the home space of that algebra will give us the fusion ring. So essentially that means we have a very interesting interpolation of that home space for the gene field center. And that's kind of a very interesting skein relation since gene field center are braided. So there we also have like a family of braided tensor categories with some very nice interpretation for certain generator relations. But we don't know whether this really can be extended to interpolated families since we don't have the full skein theory. And there somehow we know the the one side here, like in your picture. It's the black side, black color side, and that's the center of PSL2 Z mod P. But we have no idea what should be on the blue wall, like quantum subgroup, and what should be the red part as the Milgauss center. We just have no idea. But that gives a hope to find the interpolated family. And if that happens, that will be extremely interesting, since if you have such an interpolated family at p equal to 6, then this example might be integral, but not a weakly group theoretical, since there's no something like PSL2 6 with this kind of neutral center.
Yeah. Yeah, this is different. I mean, there are various, and there's these interpolation categories that are like Deline's ST, but for right, yeah, that's like GLNFQ, but then you vary the you vary the N.
Yes.
Right? Yeah. That's right. Here you want to vary the Q. Yeah, it's an interesting question.
Any other question? Okay, let's thank Noah again.
Thank you very much.
Thank you, Noah. It's great.